Welcome everyone to this second lecture of week 2 for radio astronomy. It's of course for running for the first time in NPTEL, and we are quite excited about it. Um, if you remember, last week we actually went through first telling you, introducing the entire course, and then we went on revisiting some electromagnetic theory, particularly Maxwell's equation, and also the electromagnetic waves, how they propagate, the Poynting vector, and also a little bit of polarization. This week we started off talking about different important discoveries in radio astronomy and some very important milestones in development of radio astronomy across the world. This lecture we are going to concentrate on defining very specific fundamental quantities of the electromagnetic radiation. We talk about the brightness, the intensity, specific intensity, flux density, etc. We also talk about how when the waves propagate, radiation propagates through a medium, they suffer emission, absorption, so there's a radiative transfer process involved in that. We talk about that. We talk about how stars radiate, how galaxies, stars emit different forms of radiation, how they're very close to something called black body radiation, what are the different limits of black body radiation, talking about Wien's law, talking about Allergen's limit, which is mostly applicable to radio astronomy, and also Stefan Boltzmann law, and ending with a concept very important to radio astronomy called brightness temperature. Okay. So this is again a similar slide as we have shown before multiple times. The entire electromagnetic spectrum is quite large than the radio band itself. What happens is most of the band, higher in frequency, lower in wavelength than radio, are actually absorbed. Radiation is absorbed in the Earth's atmosphere, and so we cannot observe those rays from the surface of the Earth. That's why we have to send space telescopes to detect any radiation at those frequencies. The gamma rays, X-rays, ultraviolet, infrared, most of it, we have to send space-based telescopes to observe them. Only a very minor fraction of the optical visible wavelength actually can be done from the ground. There also a lot of effects comes because of the Earth's troposphere, the water vapor content of the troposphere. And that's why you will find most sensitive optical telescopes to be housed on a very top of the mountain at a very higher altitude. We are lucky in radio that we observe most of our band without any hassle from the atmosphere. Only if you get to very lower frequencies, as ionosphere becomes a problem. If you go to a little bit higher frequencies, mostly towards the microwave, the troposphere starts becoming a problem. But most of the band we can observe from the ground. And so that's the advantage. Now, what we observe? This is a very latest and the greatest image from LOFAR telescope. LOFAR is a telescope which is located in Netherlands and expanding to other parts of Europe. And this is an image made at 150 megahertz or 2 meter wavelength. Now, this is a huge part of the sky. Definitely, the image represents a 2D projection of a 3-dimensional sky. We cannot see the distance towards from line of sight because we are only observing from one angle. So the extent is large. You cannot see much in the central image, but you can zoom in, zoomed in version of the central image based on this kind of squares are actually shown in the periphery. So you can see there are lots of structures, very important stuff, radio galaxies, jets are being observed. So what do we observe? We see there is a spatial extent in 2 dimensions. In X and Y, you can say, but we astronomers define it as right ascension and declination. We will talk about that later on in later weeks to come. And what else do you see apart from the two-dimensional extent? We see there is a third dimension, the color coding of the image. You see that there are places where you see higher values than the other places. That means the emission is not uniform across the entire spatial scale. Something is happening more vigorously and some places than the other. Okay, there are much low level emissions extending over a larger places, but very high level emission located, concentrated at some locations, particularly in these hotspots, which we call. How do we make sense of this? Unless we actually understand, go beyond and understand some critical definition of the radiation. Okay, so let's start doing that. Astronomers study an astronomical source by measuring the strength of its radiation as a function of direction of the sky, means the spatial location, frequency. We will come later. It's under spectroscopy, plus other quantities, time, polarization, etc. So depending on what you are doing, you can either be just mapping the sky, so looking at the image. You can see as a function of frequency. There also things change. Supposedly you have some particular transition, atomic or molecular transition, that will only be detected at a particular frequency. So depending on where you're located, how far away from us you're located, the source is located, it will appear in a particular frequency based on that. There are other things like time and polarization. Like so, some features are visible only in a polarized manner. Some emissions are polarized, some are not. Okay, uh, time varying. There are things which are transients, which are only visible in some time and not visible on the other. Like pulsar, when it rotates, sometimes you see, for another time you do not see. Depending on the pulse period, the rotation period, and the duration of the pulse, you can either see it or miss it. So it is kind of a transient. Latest, there is a huge uproar of something called fast radio bursts, FRBs, also transients in radio. There are other transients in other part of the wavelength, like gamma ray bursts. Okay, so these are really varying in time. In a particular time, you will see a huge amount of radiation emission, and then suddenly it falls off for the others. So that's how it is quantified spatially, frequency in frequency domain, also in time and polarization. So there are four different domains. Clear and quantitative definitions are needed to describe the strength of the radiation, how it varies in direction, frequency, and distance between the source and the observer is required. Consider the simplest possible case of radiation traveling from a source through an empty space. So there is no absorption, no scattering or emission along the path of an observer. It's purely vacuum or free space. The angular size of the sun depends on the distance between the sun and the camera or the telescope, but the number of photons falling on the detector per unit area, per unit time, per unit solid angle does not. The photo taken from near Venus would not be overexposed, or one from the Mars will not be underexposed. Total number of solar photons from all directions reaching the camera per unit area, per unit time does decrease with increasing distance, but that is because only that if you see the sun emits, it emits in all direction. So if you go further away, you are only intercepting some part of the solid angle, so that flux may decrease, but not decrease because of the distance per se. So we distinguish between the brightness or intensity of sun's radiation, which does not depend on the distance, from apparent flux, which does depend on the distance. Okay, so these are the critical things which will come. It's pretty confusing actually to begin with. Something depends on distance, something doesn't. What are we doing? So let us go forward and understand a little bit more of the entire formalism, so that will make it much more clear. So we define total brightness is the contribution of photons of all frequencies. So if we sum over all the frequency of emissions, so in different frequency, there are different emissions, as we see that the entire electromagnetic spectrum is full of such radiations. So here also, even with the radio band, we have to take into account different frequency ranges. Only then we can get the entire information. The brightness per unit frequency is called specific intensity. So brightness is total contribution of all photons emitted in all possible frequencies. Brightness per unit frequency range is called specific intensity, also called spectral intensity, also called spectral brightness, depending on who writes the book or who is writing that. So the notation is I sub nu, where the subscript nu is used to indicate per unit frequency range. So that's the definition. Let's go a little bit further and try to understand. We'll come back and again keep explain it more lucidly. So I nu is the specific intensity. Now let us see how it does. So we have a simple cartoon that there is d sigma, which is the infinitesimal area of the surface, okay, and we have a direction I in the towards I nu, and it is making a solid angle of d omega, okay. So the infinitesimal power intercepted by the surface d sigma is given by this dp is I nu, which is specific intensity of the source, cosine of theta d omega d sigma d nu, where dp is the infinitesimal power in watts, d sigma is the infinitesimal area of the detector in meter square, then bandwidth is in hertz, and theta is the angle between normal to d sigma and the direction to d omega. So that is the thing, and I nu is the brightness or specific intensity in watts per meter square per hertz per steradian. When we define this, it's a very interesting anecdote. In radio, just to make sense of how the radio signals from the cosmic sources are there compared to any of the cell phone emissions or anything like that. So the definition of the unit of this intensity is in Jansky, and that 1 Jansky is 10 to the power minus 26 watts per meter square per hertz per steradian, etc. So you understand that in typically the cell phones or even any gadget, it's milliwatt units are really where they operate even higher, and this is 10 to the power minus 26 watts. So about 23 orders of magnitude lower in the emission, in the strength to this signal. So that's why if you have any electronic gadgets, most of the telescopes are in radio quiet zone, no transmission from any other things, otherwise you kill the signal. Okay, carrying on. Intensity, brightness and specific intensity. So intensity, often termed as brightness, in astronomy, it's essentially measurement of the electromagnetic radiation. This measure has the property that it does not decline with distance, defined in such a way that it remains unaffected by the spread of the radiation also. This measurement is the quantity of the energy of the electromagnetic radiation traveling from a finite size portion of the source to a finite size portion of the recipient or the detector. Example of small circular region of the sun as seen in the sky that covers a specific angular diameter of the sky, then the EMR or electromagnetic radiation from that portion of the sun striking at a specific plot of the ground has a particular intensity, and if the sun were closer or somewhat further, the intensity from that angular diameter would remain unchanged. Some way to explain this particular phenomena, that if the definition of intensity is such a way that no matter whether it is closer or farther, that the intensity remains the same. Okay. Uh, so we have the previous definition. We have this dP, the power intercepted by the detector for unit solid angle, for unit surface area of the detector per unit frequency range. Um, that is there, and cosine theta is just the alignment projection to that direct line of sight. So we can just change the rearrange the variables and find that I knew the specific intensity can be given in terms of the power over those many terms. If you integrate the power entire thing, so this is basically the power over the area of the detector over the solid angle over the bandwidth times the cosine of theta, which is the angle which it makes to the line of sight. So what is that? Okay, so again we are writing the same expression. We are defining now the flux density, the next important quantity. Intensity is defined. Remember, it doesn't depend on the distance. Now what about flux? Flux is defined in a way that so we have the same expression as of before, the infinitesimal power intercepted by the detector, and now we are just substituting this d sigma d nu on the left hand side, and you get I nu cosine theta d omega. If you integrate, if you have an extended source, then you integrate over the entire solid angle, and you get total integrated intensity through that solid angle towards that line of sight, and you get something called flux density. So S nu is basically integral of I nu cosine theta d omega. Okay, now this is the flux density. All right, so that is the integration over the entire solid angle. Okay, so and then if you want to integrate over the entire frequency range, then that is also possible. The total flux is S nu, which was per unit frequency times delta nu, integral of that. So that is the flux density. So now, will flux density depends on the distance? Intensity was not. But will flux density depend on the distance? That's a good question. Think about it. We'll come back and answer it. So, then we define something called specific luminosity, which is total power per unit bandwidth radiated by a source at a frequency of nu. Its MKS units are watts per hertz. Okay. So the area of a sphere of radius d is 4 pi d square. So L nu is linked with the flux density by L nu equal to 4 pi d square S nu. Note that some radio sources emit beamed quasars. For example, in this case, this equation cannot be used to calculate total spectral luminosity of a beamed quasar with only flux density measurement made towards just one direction. So if it just towards one direction, then these measurements are wrong. Only if there is a source which is emitting isotropically, then this kind of treatment is valid. So that goes for that. So we are assuming the solid angle, the measuring over the entire solid angle, or per solid angle, the emission is the same in every per solid angle direction. So if a particular source has a beaming direction, so it basically has a specific emission towards one direction over the other from the source point of view, then this treatment doesn't work. This assumes that the source is emitting equally in all possible directions. That's why this per solid angle concept comes when we talk about the detector. Same thing is not true for the beamed quasars, which is which have a very narrow angle of emission. It's an intrinsic, so luminosity is an intrinsic property of the source and is independent of the distance. So luminosity is not dependent on the distance, but S, the definition is such that it is dependent on the distance, because S is L over 4 pi d square. So S depends on the distance. Similarly, if you can tell from here also that S was depending on the distance, because as the distance goes further, the solid angle decreases, and so the I nu is independent of the distance, so S will depend on the distance because of the solid angle dependency. Alright, total luminosity L of a source is defined as the integral over all frequencies of the spectral luminosity. So spectral luminosity is per unit hertz. So total luminosity or bolometric luminosity is basically integral of the specific luminosities for every given frequency intervals, and so you define over the entire range of frequencies. So you also note that for the black body luminosity, we will come later in the next lecture about Stefan Boltzmann law in more detail, but here we're just relating that L is related to the T, the temperature of the black body, as sigma A T to the power 4. Sigma is the Stefan's constant. We talk about it more later. For stars which are lying on the main sequence, that's a particular class of stars. Luminosity also related to the mass appropriately. So L and M, the mass and the luminosity, and has a specific relationship. So L over L solar. So as we're defining things in the astronomical scales, the mass of the cannot be anymore in kgs or gram. It has to be in terms of the mass of a star, of the sun. So M is over M sun and L is over L sun. So it's just a kind of a unit. We remember it easier. So L over L sun is M over M sun to the power 3.5 for main sequence stars only. This is just a mass to light ratio. So supposedly you have information about mass, you can infer the luminosity, you have, and do vice versa. So you have a higher luminosity, you have a higher mass, and vice versa. So these scalings are very powerful tools which keeps coming back and forth to the our astronomical literature, because it makes us easy to interpret the results. These are a little bit hand wavy, sometimes mostly derived from correlation of data, like we have observed this at this particular frame, so it is a correlation, and but these are very powerful tool in interpreting results from different observations. So very easily you can relate it now from something called intensity, which you are observing, to the mass, okay, of the object, and this things works very. Let's take a few examples to sort out these issues, any issues regarding this confusing definitions of specific intensity, flux density, and luminosity. Okay, so the first one, we are just trying, which of the following statement is true? Specific intensity is directly proportional to the frequency. Intensity is inversely proportional to the frequency. Total flux density is independent of frequency, and specific intensity is equal to the mean intensity. So the answer to this question is total flux density is independent of the frequency, because we know total flux is integration of S nu over d nu. Okay, so that is the true answer. Let's try one more. Specific intensity is also known as source brightness, mean intensity, brightness temperature, none of the above. And now specific intensity also called source brightness by the definition. Now some problems. Calculate the power received by the detector of area of 50 square meter, receives mean intensity of 0.005 watts per meter square when the source is at zenith. So this is the same classic example where we relate the power with the specific intensity multiplied by the area of the detector by the solid angle by the bandwidth. So mean intensity of the source or specific intensity is 0.005 watt per meter square. The area of the detector is A is 550 meters square. So the power received is nothing but 4 pi steradian times the Im times the area times cosine of theta. Remember, cosine of theta is the theta is 0, right? Because it was at zenith. Source was at zenith. So cos theta is equal to 1. So it's 4 pi times Im times A, which should give you 3.14 watts. Next example, what is the source brightness if the power received by a circular detector of radius 5 meter is 70 watts when the source is at zenith and subtends a solid angle of 15 steradian over a bandwidth of 100 megahertz. Okay, so similar problem, little bit different in the framing. So here we have given the power, the radius of the detector, circular detector, so area have to be calculated. Solid angle is given 15 steradian and the bandwidth is given of 100 megahertz. So P is 70 watt, steradian, solid angle is 15 steradian, and area is A is pi r square since it's circular. So pi 5 square, which is 78.53 meters square. Hence the source brightness or the specific intensity is given P over A sigma cosine of theta, which is 0.059 watt per meter square per steradian. Okay. Next problem is coherent measure radiation from a source at a distance of 2.3 kiloparsec has a flux density of 103 Jansky over a frequency band of 1 kilohertz. If it is isotropic, what is the power radiated? So we have given the distance of the source, the flux density is given, and a frequency band is given. It is told it is isotropic. So what is the radiated power? So for an isotropic emitter, we know that the L, the luminosity, is dependent on the flux density by 4 pi d square. So here the distance is given as 2.3 kiloparsec. 1 kiloparsec is 10 to the power 3 parsec, and 1 parsec is 3.09 10 to the power 16 meters. So if you put everything in there, it is 7 into 10 to the power 19 meter is the distance comes out to be. The total flux is specific, the flux density times the bandwidth. So 103 Jansky times 1000, 1 kilohertz. So that is there. And then 1 Jansky is 10 to the power minus 26 watts per hertz per meter square. So that is what it's given. So it is 10 to the power minus 20 watts per meter square. So L, the power radiated isotropically, is given by 6 10 to the power 20 watts. The last example, and quite a large one, a radio source at a distance of 20 megaparsec. 1 megaparsec is 10 to the power 6 parsec, and 1 parsec is 3.09 10 to the power 16 meter, is observed by a detector having area of 300 meters square at a frequency of 22 gigahertz with a bandwidth of 250 kilohertz. The source is determined to have a flux density F nu at this frequency of 10 Jansky, and is found to be of a uniform circle with an angular diameter of 30 arc seconds. So what is the intensity of the radiation from this source at this wavelength? What is the total power of the radiation detected by the detector? What is the luminosity of the source over the observed spectral range, assuming that the radiation is isotropic? So calculate I nu, power, and luminosity. So let's take the first one. The average flux density is divided by the flux density divided by the solid angle of the source, and since the source is found to be an uniform circle, the intensity equals the average intensity. We first need to find the solid angle, since we are only given the angular diameter using the relation as below. So since it is 30 is the diameter, so theta by 2 is the radius. So we figure out the solid angle, and that comes out to be 1.66 10 to the power minus 8 steradian. The intensity then is just simply the flux density 10 Jansky converted to the watts per meter square per hertz per steradian into that unit, and then divided by the total solid angle, which is 1.66, divided by multiplied by 10 to the power minus 8 steradian. If you put the numbers, it comes out to be 6 10 to the power minus 15 watts per meter square per hertz per steradian. That's the I. Okay, number 2, the second question was total power of radiation detected by the detector. So the first part is I nu remains the same. The P nu is nothing but the flux density multiplied by the area multiplied by the bandwidth, and that comes out to be 67.5 10 to the power minus 18 watts. That's the power. We have a third question, which is what is the luminosity of the source observed over the observed spectral range, assuming that the radiation is isotropic. So S nu, the flux density, is total flux over delta nu, and also S is luminosity over 4 pi d square. So given that, we can relate the specific flux, luminosity over the entire range to be equal to the flux density times the bandwidth times the 4 pi of distance square. If you put all the values, distance is, remember, it's 20 megaparsec, 20 times 10 to the power 6 times 3.09 into 10 to the power 16 meter. So if you put all the numbers, it comes out to be 2.4 10 to the power 29 watts. So this brings us to the close of another lecture. I hope that these specific problems which we tackled in the end actually helped you to little bit understand more and de-entangle the issues between flux density, intensity and luminosity. But we will discuss this more all through the lecture, the series, and hope it helps. Thanks for joining, and see you on the next lecture. Thank you very much.